Friends, today we are going to discuss about Fraunhofer diffraction. Fraunhofer diffraction, single slit. We are going to discuss about Fraunhofer diffraction, single slit. In the case of Fraunhofer diffraction, the source and screen are at infinite distances. That's why by using two convex lenses, one convex lens is used as divergent lens and another convex lens is used as convergent lens. By using divergent lens, parallel light beam is made to travel through the slit, and by using another convex lens, the diffracted beam concentrated at different points. That is the basic idea in any case of Fraunhofer diffraction. Now, in the case of Fraunhofer diffraction, the incident beam is a plane beam. Instead of plane beam, that is plane incident wave is used in the case of Fraunhofer diffraction. Now, let it be the single slit. Here AB is the single slit. Now, plane wavefront is incident on the single slit. Let it be the plane wavefront. This is the plane wavefront. This is the direction of waves. That is, this is the direction of light rays. And again, this is the plane wavefront. Here, this plane wavefront is obstructed by this single slit. Because of this obstruction, here each point on the wavefront, according to Huygens theory, each point on the wavefront acts as a source of secondary waves. These secondary wavelets interferes and produces diffraction pattern on the screen. Let it be the screen or photographic plate. Let it be the screen or photographic plate. Now, here we are using a convex lens here. Actually, another convex lens is also there here. That convex lens produces parallel light beam, and again this convex lens acts as convergent lens and converges the light rays at different points. Here, how diffraction pattern is formed? Here there is a plane wavefront. Part of this wavefront is obstructed by this slit. Because of obstruction, each point on the wavefront acts as a source of secondary wavelets. These secondary wavelets interferes and produces diffraction pattern on the photographic plate. Now, we are considering 5 rays here. Let it be 1, 2, 3, 4, 5. Here we are taking an example only. Actually, the width of the slit is extremely small, and again the number of rays is extremely large. That is the real case. Now, here that the middle ray travels directly through the lens and incident at a point P0. Here there is no path difference here. There is no path difference here. Path difference is 0. That's why maximum intensity is formed at P0. It is termed as central maximum. Now, diffraction takes place at the edges. Suppose a light ray travels here, and again because of diffraction, here it is concentrated at some other point P0. Now, another light ray here travels here, it concentrated at P0, and again another light ray travels here and it concentrated at P0, and again it concentrated at some other point. Let this point be P1. Here above P0 and below P0. That is, diffraction pattern is formed above P0 and again below P0 also. Here, why this diffraction pattern is formed? Because of this wavefront is obstructed by the slit. Wavefront is obstructed by the slit. Because of diffraction, bending of light rays or change in path of light rays takes place at the edges of the slit. Here P naught is the central maximum. We can draw lines below P naught also. Diffraction pattern is formed above and below that of P naught. Now coming to theory, let AB is the single slit. Let E be the width of the slit. Let E be the width of the slit. Here AB, this is the position of AB. Because of diffraction, there is a change in path that takes place. Now suppose we are drawing a perpendicular here, let it be C. Now here it is a perpendicular, here it is 90 degrees, here it is the deviation, let this point be theta. That means here it is the point, this is theta. Let this point be theta. Since it is 90 degrees and again here it is also again theta. These two are perpendicular to one another and again these two are also perpendicular to one another. These two are perpendicular to one another and these two are also perpendicular to one another. Then sin theta is equal to opposite side, that is BC by AB. Then BC is equal to AB sin theta. Here AB is the width of the slit which we take as E, which is equal to E sin theta. BC is equal to E sin theta. Here it is path difference. Here path difference is equal to E sin theta. Now phase difference is equal to 2 pi by lambda into path difference. Hence it is 2 pi by lambda into E sin theta. Now suppose there are n equal parts in this slit. Suppose there are n equal parts in the slit. Now suppose there are n equal parts in that slit. Why we are taking n equal parts? Because already we have derived an expression that is resultant of n sinusoidal disturbances. Amplitude of n sinusoidal disturbances is R is equal to A sin nd by 2 by sin d by 2. This is the resultant amplitude of n sinusoidal disturbances. The equation is derived in the last class. You can observe it. Now, when there are n equal parts, then phase difference becomes 2 pi by lambda 1 by n E sin theta. Here in this expression phase difference is d. That's why 2 pi by lambda into 1 by n into E sin theta is equal to 2 pi by lambda into 1 by n is equal to d. Right? Now R is equal to A sin nd by 2, which is n by 2 into d value 2 pi by lambda 1 by n E sin theta whole by A sin d by 2, A sin 1 by 2 into d value 2 pi by lambda 1 by n E sin theta. Okay. How this equation come across here? Here it is the resultant amplitude of n sinusoidal displacements. Those n sinusoidal displacements are represented as y1 is equal to A sin omega t, y2 is equal to A sin omega t plus d, y3 is equal to A sin omega t plus 2d, so on and so forth. Yn is equal to A sin omega t plus n minus 1 into d. Here A amplitude, d is the phase difference. By using these aspects, we came to an expression for amplitude is resultant amplitude is R is equal to A sin nd by 2 by sin d by 2. Okay. Now we are using this expression here. Here D is the phase difference. That's why phase difference is taken as D here. Now R is equal to, from this expression, now R is equal to A sin nd by 2. Here n gets cancelled here and here, 2 gets cancelled here and here. A sin pi e sin theta by lambda, pi e sin theta by lambda here, whole by sin a. Now sin 2 gets cancelled here and here, pi e sin theta by lambda into n. Now suppose we are taking that pi e sin theta by lambda is equal to alpha. Pi e sin theta by lambda is equal to, now put pi e sin theta by lambda is equal to alpha. Then what happens to the denominator? Pi e sin theta by lambda into 1 by n. That's why resultant amplitude R is equal to A sin alpha. Alpha means pi e sin theta by lambda whole by sin alpha by n. When alpha by n is small, sin alpha by n is nearly equal to alpha by n. Then amplitude R is equal to A sin alpha by alpha by n. Now resultant amplitude R is equal to Na sin alpha by alpha. Suppose Na is equal to capital A. Why we are taking like this? Here in the case of diffraction, the size of the width is extremely small. That's why n tends to infinity and A value is extremely small. A value is extremely small. Then Na is a finite value. In that context, we are taking that Na is equal to capital A. Then resultant amplitude R is equal to A sin alpha by alpha. Now what happens to intensity? Intensity is proportional to square of amplitude. That's why intensity I is equal to A square sin square alpha by alpha square. That's about intensity. Now conditions for maximum intensity and minimum intensity. Conditions for maximum intensity and minimum intensity. Now from this expression, R is equal to A sin alpha by alpha, which R is equal to A by alpha into sin alpha. Sin alpha expression, sin alpha is equal to, actually we can write the expression for any trigonometric function sin theta, cos theta, tan theta or exponential function e power x by using Taylor series. According to Taylor series, for any function f of x, series can be written as f of x is equal to, at a particular point a, f of x is equal to f of a plus x by 1 factorial into f dash a plus x square by 2 factorial into f double dash a, so on and so forth. Rn, where Rn is termed as remainder. In this case, f of x is equal to sin x. By making these expressions, sin alpha is equal to, expression for sin alpha is, expansion for sin alpha is alpha is equal to alpha minus alpha cube by 3 factorial plus alpha to the power of 5 by 5 factorial, so on. By substituting all these values, we get it as sin alpha, A by sin alpha, this is alpha minus alpha cube by 3 factorial plus alpha to the power of 5 by 5 factorial, so on. Now R is equal to A into 1 minus alpha square by 3 factorial plus alpha to the power of 5 by 5 factorial, so on. Now amplitude becomes maximum when alpha is equal to 0. Amplitude becomes maximum, R is equal to A, when alpha is equal to 0. What is alpha? Alpha means pi a sin theta by lambda is equal to alpha, which is equal to 0. That means sin theta is equal to 0. Sin theta is equal, in this expression sin theta is equal to 0. Now actually pi a sin theta, that is actual expression is r is equal to a sin alpha by alpha. When alpha is equal to 0, intensity is maximum, that is central maximum. For minimum condition, r is minimum when sin alpha is 0. When sin alpha is 0 is the maximum. When sin alpha is 0, alpha is equal to plus or minus m pi. That's why, suppose we are drawing a graph between theta or alpha on x-axis. Suppose we are drawing a graph between theta or alpha on x-axis and intensity on y-axis. Theta or alpha on x-axis and intensity on y-axis. Here there is a central maximum and again this is central maximum when theta is equal to 0. It is minimum, then sin alpha is equal to 0 means plus or minus m pi. This is plus pi and this is minus pi. Again minimum plus 2 pi minus 2 pi and so on. These are termed as secondary maxima. These are termed as secondary maxima. Secondary maxima occurs when di by d alpha is equal to 0. By equating the value of di by d alpha is equal to 0 by making differentiation of total intensity. Total intensity A is equal to a square sin square alpha by alpha square. By using that expression, by making differentiation, we get secondary maximum. Now, final conclusion from this graph is, here P0 is the central maximum and again minimum takes place here. Minimum takes place when theta is equal to plus or minus m pi. That is when m is equal to 1, plus pi minus pi on both sides. And again plus 2 pi minus 2 pi on both sides. This is the condition for minimum, intensity minimum. And again there is another maximum here on either side, that means on left hand side and at the same time on the right hand side also. These maxima are termed as secondary maximum. This is principal maximum. These are secondary maximum. Secondary maximum place means here is pi, 2 pi in between these two. That means at 3 pi by 2. And again at 5 pi by 2. Here also minus 3 pi by 2. Minus 5 pi by 2. And again diffraction pattern is formed on either side. The same thing is explained primarily. That is, in the case of primarily, this is the mathematical expression. Here we have a single slit like this and plane wavefront incident here, which is obstructed by the slit. Again you have a screen. Here you have central maximum P0. This is the central maximum P0. And again here you have some other point. Here a convex lens is placed here. Here you have some other point because of diffraction. There is a bending at some other point. You get P1. P1 on right upper side of y-axis and lower side of y-axis. Here also secondary maximum. And again this is primary or principal maximum. These are secondary maximum. In this way, single slit, we are explaining the aspect of single slit. The same thing can be explained in the case of double slit. That means 2 slits. If there are n slits and slits are very close to one another, that is termed as grating. Grating is nothing but combination of n slits. In practical grating, the grating that is used in our laboratory, you can observe that it is written as 15,000 lines per inch. Inch means 2.54 centimeters. In 2.54 centimeters, there are 15,000 lines. That means in 1 centimeter, there are 5906 lines per centimeter in 1 centimeter. That's why a large number of lines. You cannot observe lines. Actually, you can observe a surface here. By using grating, we can produce, by placing the grating in normal instance, we can get, we can produce, and at the same time we can determine the wavelength of spectral lines. Wavelength of spectral lines. Next aspect is determination of wavelength of spectral lines using grating. Before going to the determination of wavelength of spectral lines using grating, we should have some simple idea about the theory of grating. By theory of grating, we coming to expressions on these lines. In these lines, here you should keep in mind resultant amplitude R is equal to A sin alpha by alpha. And again, here central maximum, secondary maxima, resultant intensity I is equal to A square sin square alpha by alpha square. By using these expressions, we can make simple expressions for grating, and by using those expressions, we can determine the wavelength of spectral lines using optical grating. Next class we will discuss about the theory of grating. Thank you.